All right, good morning. So I suppose today you have your first quizzes, right? Some of you already had it this morning. Hopefully not a big deal. The GSIs will tell you about the details of how it's all going to work out, but I think it's just going to be homework problems and not much to worry about. Many questions about calculators, and I say it again, I think I said it the first day, that the homework problems in the book are very calculator-based. It's a lot of sine and logs and stuff, right? And on the exam, you're not bringing a calculator. So clearly, I'm going to have to ask the problem somewhat differently. I'll pick numbers such that you can do simple arithmetics. Maybe it will be more algebraic. You'll see. I'll post old exams later on. You'll see what's going to happen. I don't think it's a big problem. But of course, when you look at the problems in the book, many of them are really calculator-based. Yeah. Is your GSI? So again, I leave them a lot of freedom for this, but I would probably recommend that they have the same conditions on the quiz as on the exams, namely no calculator. But again, I leave that just to get practice for that nature, right? So I guess the problems they pick will also be done something you can do by hand. Also MATLAB. I mean, a MATLAB is a calculator. So the question, can I use MATLAB, is yes, you can as a calculator. The only issue I want to avoid is that since I post all these functions, like for example in your most recent homework, fixed point iteration, right? We just want to make sure you just don't run it and write an answer and you're done. So your GSI, you'll get a feeling, but you need to convince the GSI that you know how to do it. Remember on the exam, I might ask you to do like 2 simple steps of fixed point, and if you then just ran a MATLAB function, you won't know how to do it. So exactly how much you report on your homework, I think it's clear. When you understand it, you can use the MATLAB. Maybe you write 2 steps and say, OK, now we continue 30 iterations, and here's the answer, right? I mean, but clearly, we don't want you to just do a lot of number crunching by hand. So we're trying to be reasonable. Just trying to teach you guys this stuff. So about what's going on here, I'll talk more about the programming assignment. Hopefully, some of you have started, and we're now almost ready to really understand exactly all of it. It's still 3 weeks left until it's due. I would recommend starting early, especially those of you who are new to programming. Even if you think you can write it easily and the code is just this long, when you make mistakes in the code, it's really binary. Either it works or it doesn't. And debugging and making sure it works, it can take hours. So it's not like a homework that is kind of close enough and then you move on. Programming, start early. I will now, as you see, we're running. I just started on Newton last time, and I have 2 to cover. And I'll do my usual trick, what I think is quite pedagogical, that we'll skip some of the proofs. And then on Thursdays, I catch up with proofs and etc., so that you're all ready for next week's problem set already by today. What else? Yeah. That's all. Any questions? Yeah.
As far as grading the homework goes, I know you mentioned that this class might have readers.
Yeah.
We haven't heard anything about that. Do you know if that's going to happen, or if the GSIs are going to end up grading the homework?
I think they learned just end of last week that they are getting graders, all of them, which means that your homework will be graded well. Now, if you look at the hours those graders are getting, it's not quite enough to go through all of your problems and give good feedback. They have a certain number of minutes per problem set. But it's certainly better than if the GSIs were grading, because then we would have to do pass or fail. So hopefully you will get, maybe they will select a subset of your problems, hopefully at least half, I think. I mean, they have a pretty good chunk of time to grade this, and at least give some feedback to where you made mistakes, etc. So that's the good news. The GSIs will be grading the programming assignments and their own quizzes, I think. More questions? All right. Let's just dig right back into this. We've dealt with fixed points over and over. You know the theorems. Don't mix them up too much. I mean, existence and uniqueness and the derivative and what else we're doing here. Remember, there's a statement about fixed points in general, whether they exist or are unique, has nothing to do with fixed point iteration, the numerical techniques for keep on stepping, or not numerical necessarily, but the idea of forming a sequence of numbers for finding a fixed point, right? But that comes then in a second theorem, which is actually the fixed point theorem, which says that under the same conditions, including the derivative condition, fixed point iteration will converge, okay? And we write fixed point iteration simply as Pn equals g of Pn minus 1 for some P0. And this is very powerful. It means that you can prove before you do it that it will work. That's kind of what numerical analysis is all about. Come up with a method for doing something useful, like solving an equation, but also do a lot of math to try to prove that it works. And whether this is applicable for real big practical problems or not can be discussed. But there's a lot of value in being able to have these theorems. We'll try to extend it to Newton today. And you have these are also great results coming out of this analysis that perhaps you can even predict how fast it will converge. And you've been training on how to do that in your homework. Let's rush on with Newton that I started with last time. We all know it from the high school, I would say, or at least freshman calculus. We just draw a straight line tangent to the curve at a point that you choose, and then we move that line down to the 0. And of course, that might be a good approximation, or that it might not. And then you take that and you keep on going. If you solve for that, you get a very simple iteration that you definitely should know by heart, namely that you take the old point minus f at that point over the derivative at that point. And that's your new iteration, and you keep on going. Where does this come from? Well, I could derive it easily, like I think they do in high school, by just drawing a triangle of height f of Pn minus 1, right? And there's a slope, which is f prime of Pn minus 1. And then we're trying to move a distance Pn minus 1, and you can get a triangle out of that. Now, maybe in this class, it might be better to see exactly what's going on. And why don't we just do, it's kind of equivalent, but we do a Taylor approximation about your point P0, which then says f of P0 plus some sort of delta x, but here we call it as P minus P0, times the derivative, plus a second order term, which is the square of that, half times a derivative. And we end it with xi there somewhere between P0 and P. Okay? And it's clear that what we're doing is, it was clear already from the beginning, we're drawing a straight line, which means that we're neglecting all the higher order terms in the Taylor. In this case, since we ended it with xi, we're neglecting this quadratic term. Okay? And then we get a straight line, and you can solve it straight out and get it. So there are many ways to derive this. In fact, we'll today reach another even more beautiful derivation of Newton. And it's good to see all these different forms to see what's going on. But basically, this is the geometric way to see it, or the Taylor way to see it, that you're putting this straight line. Let's run a little bit. Here, I put the MATLAB implementation here. This is also, again, so simple that I think you should almost write it yourself. But this is more to demonstrate how simple things can be done in MATLAB. What would a function called Newton need as inputs? Remember, fixed point needed a function g. We wrote that before. Actually, bisection needed an f. So we're used to sending, we already seen sending functions in. Of course, if we want to solve fx equals 0, the user must provide f, right? Now, if you look at my header up there, I'm also asking for df. And it should be clear from that name. I like my short names, but it should be clear what I mean, namely f prime. Why do I need it? Well, Newton needs it, right? Couldn't I compute it on the fly? That's a big if, right? That's something called symbolic algebra. That's not really what MATLAB is in the business of. So you got to differentiate. And this is one of the drawbacks with Newton. And it's clear from the method. There's a big derivative there. You need both f and f prime in order to do it. Now, this might not be this is actually not a big problem for any of your, I shouldn't call it toy problems, but the examples that we do from the book, because you usually have f and it's easy to differentiate. But I think I mentioned last time, f could be a black box. It could be data collected from some measurement equipment or something. F prime might be an issue. Having said all that, you need df. From the point of view of this function, we just ask for df. What else do we need? We need a p0. Remember, Newton has no a comma b. There's no bounding. There's nothing like that going on. It's a p0 where you start, and you get what you get. And we'll see that sometimes it really doesn't work. There's some sort of tolerance. I mentioned before, tolerance and quitting these iterations is a huge issue. Nothing is perfect. This is definitely not perfect. We can see exactly what I do. But it's quite straightforward. I take a step of Newton. And it turns out that the tolerance I'm doing now is, in words, if the step Newton took is small, I call it quit. Is that a proof? Does that mean that I'm close to the true solution? Depends on the function. Just if you want to think about it, you can think. Usually it's kind of OK. But think of this. You have a 0 here that you're looking for, but you're standing here. OK? You're going to have a Newton step that brings you a very short distance over there. And it might be that you say that this distance between P0 and P1 or whatever is very small. But you're really far away from this. And that happened because the derivative of the function was large. So it's not perfect. Nothing is perfect. Whatever you come up with, you could almost break it. Someone suggested last time very correctly that why don't we look at the function value, f, and see if we're close. But again, then the example of that would be a function that looks like this, where you could have, this is the true root, but if you're over here, the function value is still very small, and you might say, hey, it looks fine, but this number could be huge. So that would fail for small derivatives of the function. These always fail. It's not a huge part of the course. It's not emphasized a lot. Having said that, we need to do something. Otherwise, our codes wouldn't run, or they would run, but they wouldn't finish, right? So we need to do something. Just don't worry too much about it. Don't mix this up too much with your nice corollary in the fixed point, which is a strict theorem, saying we guarantee that the error, I'm talking about, where am I? Here. We guarantee that the error is less than this, right? Which requires you to know a k, perhaps taking a step and then doing this or this, right? This is really a proof. My termination here in Newton, as I just showed here, you can come up with cases. Oh, I'm mixing up, sorry. You can come up with cases where it really doesn't work. So this is just one way to quit. And in general, if you don't, I mean, without knowledge of what's going on, it's hard to give good estimates of this. I have some functions. Let's look at my examples. So we have this Newton function, as I just showed. As you know, I like to provide something that you will probably base your functions on. Let me just do format compact. So I create a function called table, very similar to bisection table for those of you who played around with that. And it does a fixed number of iterations, and it prints some stuff, right? So we'll try this function. I also wrote a function called plot, which it does a lot of stuff. You don't want to read. Don't freak out if you don't like to read MATLAB. It plots, and it does this usual thing of plotting tangents. So we can look at that too. And then I also need some extra input. But let's take a simple example. You know how I like to keep it as simple as possible, but still representative. So I'm not going to solve f of x equals x. Why is that a bad case? It's a little too simple, right? What will Newton do? I mean, f of x equals 0 is really, it has a lot of, it's a weird function, right? It has a lot of, so, but x is the next simple one. Will Newton work on it? I think it will be OK. What do you think? What would it freak out about? There is something to what you're saying, but if you don't, yeah, that's just MATLAB technicality. Yeah. I mean, just mathematically, it will go here and it will approximate the true function by a straight line, by a Taylor according to the slope. That is the true function, right? It will exactly. There are no second order terms. The Taylor second quadratic term is 0, right? So it will take the true line and intersect and find the 0. It kind of works. It's boring because it works in one step. So then maybe what about x2? F equals x squared with a 0 at x equals 0. Is that a good test? You don't know that yet. It's an interesting example. It will not convert in one step. And it's actually it's one of the cases where Newton is doing poorly. So we'll come back to that later. So let me do my favorite from before. Remember I solved x equal cos x? I like that. I'm going to do that again. Frequently asked question. Why didn't MATLAB freak out when I wrote that? That's not MATLAB. That's not OK syntax in MATLAB. I didn't press enter. I pressed Control-C. I'm just communicating that equation by you. If you want to write something, you should really use comments like this. Then you're allowed to press enter. Okay? This is really just a MATLAB detail. So how did we do this? So can I solve? Remember, this was g equals cos of x, right, in the fixed point language. Now, we're not doing fixed point now with Newton. Turns out we will analyze Newton as if it was a fixed point iteration later. But if you really think about Newton, it has nothing to do with g. It has to do with an f that is equal to 0. So you better rewrite it. So I would suggest doing this. Right? Write the function f. That is the thing you want to find a 0 to. Very simple. And remember, we insist that you differentiate this. Otherwise, the function just won't work. So you better do that. And you need to know how to do that. And we'll discuss ways to get away from that later. But for now, let's just do that. And now you can run a Newton table. And it wanted f. You see MATLAB is giving this help about that's kind of nice. It wants a df. It wants a point to start. Remember, we started at 1 for the fixed point. Why not do the same now? Newton table doesn't want a tolerance. It's going to do a fixed number of iterations no matter what. Let's do 5 iterations. OK? And here's a table. It's showing 1 line per iteration. It's showing an approximate p, which is the p we're at right now, right? Remember, I told you before, I often change notation. When we write math, p, I usually let denote the true actual root. But now, for convenience, it corresponds to the iterates that we in math notation call p sub 0, p sub 1, etc. Okay? So it is sometimes confusing about that. Even worse, there is a p0 there. What do I mean by p0? I mean the previous step. Okay? So I just rename things. You have to read the code to see what I do. Luckily, the code is like 1 line or 2 or 3. So you can see what I do. But don't take for granted that the notation corresponds to the math, because it's usually not easy to do. Because, for example, we can't do p sub 1 easily in MATLAB. We could, I guess. But anyway, what do we observe? It seems to converge to a number. By just looking at p, the 3 last lines, it seemed like it doesn't change much, right? Which is a possible indication that it really nailed our root very quickly. Although, as I said, you never really know. Of course, by plotting, what I'm doing here is that I'm looking at this step that between the current and the previous iteration. And it seems that it goes down to 0. So yeah, I mean, this looks pretty good. And maybe what you notice compared to the previous fixed point iteration example is that, wow, this is extremely fast convergence. It's just a very, very good method. So we have to understand this a little bit more. Let's go back to this plot that I mentioned, just for understanding it. Why doesn't it give me feedback? What did I do to get feedback? I don't know this GUI. Anyway, I remember it. It wants a point to start. Let's say 1. And it also, in order to plot, it needs to know which numbers you want. So let's do -1 to 2. You'll see what I mean by that. And let's move this window away a little bit, so we get room for the plot on the right. And let's run it. You see the red line? Well, it's not that interesting. It starts at 1. So the blue curve, not the 0 line. I'm plotting the 0 line because that's the intersection that we want to find of the. But the curved blue line is, of course, the function f. And we want to find the 0. The red line, we start at 1. We evaluate f. We do a tangent down to 0. It looks like in one step, it's visually perfect on this plot, right? So it's kind of a cool method. But it doesn't really show how it can then nail it with 8 digits in 3 iterations. So this plot doesn't show everything. We can use this plot, though, for seeing what happens if we go further away. I did say already before by some examples that if you start here at a 0 derivative, Newton will explode. It's not even defined, right? So you better avoid 0 derivatives. But it's worse than that, because, I mean, what are the odds? You could say, I'm not going to pick a 0 derivative. But if you go too far away from the root, things are going to go quite bad. So let's go up to 2 and see that that works great. Isn't that amazing? I mean, just almost as fast as before. It just goes straight in there. But of course, in a relative sense, you see that this blue function really looks like a straight line all the way up to 2. So you shouldn't be too impressed about that, because we're approximating something that is almost a straight line by a straight line. So it's not too impressive. Let's move on, and I'm going to zoom out a little bit like this. So we're going to run this case. What if I go up to 3 now? So this is still 2. I'm just zoomed out a little bit. Actually, let me zoom to the left as well, because I know we're going to need it. All right. So here's the function we're trying to solve. And it has a lot of issues. And that's why I meant that it's a great test case, because it can demonstrate all these issues. So what about 3? Here's 3. That could have gone really bad, but it worked out. You see? The slope is going away a little bit from, you see that the slope is approaching 0 up there. And I actually, as soon as it does that, I run far away. It threw me all the way over here. And it could really easily have ended up in a bad region here. But luckily, it brought me back inside and to the closed area. So I was lucky. But this is really as far as you can go. 3.5. Oops, now my zoom was bad. So clearly, by experiment, we see that Newton is not guaranteed to converge for any initial condition, which we knew, of course, right? Now, having said that, it's remarkably good for many cases. It's good just we can look at the function again. So you want to stay away from those values. We need some sort of theorem. We need to analyze this. And the good thing is that we've already done it with all the fixed point material. We're just going to try to apply that to this Newton iterations and see how it works. The idea here is, of course, to say that if we're close enough in some sense, it's going to converge. We'd like to say something very similar to the fixed point, that we could set up a scenario where we say we know it will converge. It turns out that it's very difficult for Newton. It's very difficult to say exact number, like these a's and b's. Depends on the function. You can do it for a particular function, but not in general. So the best theorem you're going to get is this. Let's look through everything. I want f to be C2. Do you have a feeling for why I need C2 here? What? Is the error? Yeah, exactly, the error term. So this theorem doesn't really talk about the error per se, but if it's not C2, it means that the second derivative could be infinite. What does this mean if the second derivative could be infinite? It means that this straight line could be arbitrarily bad. We can't allow that. Then it could blow up to, this could be an infinitely heavy weight that you're discarding here. And it will show up in the analysis. I'm just giving you a hand-waving intuition for why it doesn't make sense to replace something by a straight line if the second derivative is infinitely large. But anyway, so we have an a and b now, just because that's going to show up in the proof. But there is a p, and there is a root, and f of p equals 0. We need to insist right now that f prime, the derivative, is not 0. That's where I said that the simple case x square seems simple, and it will work, but it has issues. We'll come back to that later. So for now, let's consider these cases where it's clear that it goes through without a 0 derivative. I don't like if it has a 0 derivative on the actual root itself. And here comes the theorem, and you'll be disappointed about how unconstructive this theorem is. It doesn't say much. It says there exists a delta, a positive delta, such that Newton's method generates a sequence converting to p for any if you start within that delta. Okay? It says exactly what we observed. In words, if you start close enough, it will converge. Okay? But no details on how close. It's hard to give precise numbers. You could do it for a specific function. We observed that 3 worked fine, but not 3.5, right? So it's really an iffy theorem in that sense. But at least it makes it strict, and we can prove that this is the case. There is always a delta. And sure enough, that delta might be so ridiculously small. This proof won't tell you that it's useful. It could be that you're so close that you don't really care about running Newton in the first place. But in practice, it turns out to work fine. But that's the theorem you're going to get. And the way we're going to prove this is to just go back to fixed point, even if everything we've done with Newton so far has nothing to do with fixed point. I hinted on Newton when we did fixed point and 0 derivatives. And let's make that connection clear now a little bit. Really just looking at Newton, remember Pn minus 1 minus f of Pn minus 1 over f prime of Pn minus 1. Plug that into Pn. That is a fixed point iteration, with a particular choice of g being x minus f of x over f prime of x. Remember when we started introducing fixed points, I said you can go back and forth between fixed point and root solving problems. I had a slide that looked like this, said that you can choose a g that is x minus f of x, and that's one way to turn the fx equals 0 into a fixed point problem, right? But you can also multiply it by minus 3 here, for example, and stuff like that. And what Newton does is a particular choice, namely, it divides it by f prime. All right, that's all good. That's what it's doing. And we're going to see why that is a good choice. And we already, again, indicated on it because it turns out that the k, the derivative of this g, will be 0 on the root. That is the trick. Remember, we tried to, for the fixed point, we liked small derivatives of g, right? Well, this is trying to make it small by dividing by the derivative of f, and it actually will make it 0. So that's what's going on. So in order to apply this, all we're going to do now is take this particular g, the conditions in that theorem, and see if we can plug it into the fixed point theorem that you know well by now because of your exercises. And that will basically tell us. We can apply and say, yes, it will converge. Unfortunately, with a very non-constructive delta. But that's OK. So let's see what we can do about that. It's pretty short, so don't freak out yet. All right, so the theorem is there. Theorem, Newton convergence. And I'm not going to repeat it. All right, let me repeat it anyway, so we have it. F in C2 between A and B. That we need. There must be a root in A and B. I said that I don't want the derivative to be 0 at that root, because that would be bad. Then there is a delta, positive, such that Newton converges. To this root P, if you start in the interval for any initial condition P0 around this value here, P minus delta, P plus delta. Okay? I really just summarized what's in the theorem. So how do we do this? Newton is fixed point iteration with g of x equals x minus f of x over f prime of x. So we go back and look at what we needed to know for the fixed point theorem to apply. And basically, we had to pick an A and a B. And it sounds like there's going to be a delta here. But when we get there, it sounds like this will be our A comma B in the fixed point theorem, right? We have an interval because we made it up. And what do we have to show? The big things are, of course, continuity. We need to actually to show for the convergence, we needed C1 differentiability, right? Because we wanted to say that the derivative was small enough. One big thing was mapping into itself. So you need to know that when you plug in a number in your A and B, it has to come back around there, or not outside that interval. And the last thing was that the derivative of this should not be too large. In fact, staying away from 1. If you show all that, then the theorem is done. That's really what it's about. And just to give you an intuition for why this is going to happen, and then we do the technical details. But it's good to know first why it kind of is going to work out. And we already discussed it. So remember that it is a root-solving problem, fx equals 0, but we turned it into a fixed point. And the big thing that we already indicated, but the reason this is going to work, is that Newton chooses it such that your g has a 0 derivative at the fixed point P. Okay? Can you see that that, with the right assumptions, will lead to everything you need? Let's say this is the window. That's, of course, P minus delta to P plus delta. Just intuitively, first of all, if the g prime is 0 at the fixed point, can you all see by continuity of that derivative, I must be able to find an interval so it's less than 1. Right? It's 0 here, maybe it's 1 over here, but then I just pick a smaller delta. But there must be a delta such that if I go a little bit away, it stays away from 1. Okay? Basically by the definition of a limit. We'll come back to it when I write it down more formally. But of course, if you have a function that is equal to 0 at the point, you need to be able to find a value where it's less than 1 in a whole interval. Next, how about mapping into itself? Well, that's also a related thing, that if you have a 0 derivative here, basically, just looking at it, it seems that it's flat enough in a region such that you should be able to pick a delta so it doesn't run out of the box. That's just intuitively, again, what we're going to show. And that's all you need. And you also need to show that this g actually has a g prime that is well defined. Do you see, by the way, why this condition comes immediately? What will fail if this wasn't true? We divide by 0, right? Or another. So then you could argue, well, we never end up exactly at p, but just strictly speaking, this g would not be continuous. might not even be defined, right? So we cannot use the theorem. So clearly we need this. We'll see what happens when we don't have that. Anyway. Well, that's why I mentioned that. We'll run it with x squared soon. X squared is a perfect test because the derivative is 0 at x equals 0. And you'll see that it works because of the reason I said. We never actually plug in the true value, except at the end it will, and then it freaks out. But it will kind of work up till then. But what we'll observe is that the convergence is not as good as we want. So we'll fix it somehow. But yeah, you can make those arguments. But according to the theorem, there are no excuses. If it's not defined at the root, we cannot use the theorem. Just reminding you that the theorem wants some pretty strict things here. It has to be C, continuous. Okay, so it would fail already there. Then, of course, we also ask that it has to have a derivative. All right, moving on. So a few steps here. So the idea is now to find an interval. And we're going to call it first, well, it's going to be the delta from the proof, from the theorem, such that, to begin with, G maps into itself. Remember, that's my way to say that G, for any number between A and B, returns a number between A and B, okay? Or staying inside the box, or whatever you want to call it. The next thing we had to show was that the derivative wasn't too large, but more precisely in magnitude is less than or equal to k, which is less than 1 for these values. OK? So let's do that. Not a lot of blackboards here, so I'll move over here. First point, the f prime at p equals 0. No, sorry, it's not 0. And f is continuous. OK? What does that mean? Here's one of those steps that you have to think a little bit about. It means that there exists a delta, and I'm going to call it delta 1, such that f prime stays away from 0 in a larger interval of p minus delta 1, p plus delta 1. OK, so this might be a little bit of a step for you guys, but here's a little drawing indicating it. So you have a function, and it's actually this f prime that we're talking about. And there's a p, and we say that it's non-zero, right? That was the condition. It could be 10 to the minus 6, but it's non-zero. All I'm saying is that, of course, it might be 0 somewhere. Remember, the goal here is to find an interval so that it stays away from because I don't want to divide by 0. So I need to find an interval where it's well-defined, where G is well-defined. And I'm not going to give you, this shows how much this theorem sucks, because it doesn't tell you anything concrete about that value of delta. But by continuity, it's basically a delta epsilon proof. I need to be able to find a delta. I will always be able to find a delta, where this is p plus delta, and this is p minus delta, such that f prime, that's some same function, it stays away from 0 in that entire interval, right? Do you see why that's true? Remember the definition of continuity, or actually one theorem we had about it, was that any sequence converging to p here, let's say just a sequence going like this, has to make these values converge to that, okay? Now from the definition of limit, it means that you can give me an epsilon, and it means that at some point in this sequence, you're going to be close enough that you never leave this band, right? Whatever epsilon you give me. That's how delta epsilon proofs work. And it's clear that I could, for example, choose delta to be equal to half of this height or something, right? So it's not very constructive, but it's clear that if you want to go from 0 up to a non-zero value, there will be a little interval around the non-zero where it's non-zero in a whole interval. So I'm really just translating a non-zero at a point and continuity into sorry, of course the function itself has to be, f prime has to be continuous, into the fact that it's non-zero in an interval. This is just a little analysis step that you have to take. And I'm going to make the same argument. So what can we do now? If we have this, that means that g prime of x. So remember, we're going to need g prime. So we're going to differentiate this. So let's do that. It's 1 minus, and there's a quotient, right? So it's going to be f prime of x times f prime of x minus f of x times f double prime of x divided by f prime of x squared. This is abusive notation. A lot of people would put a bracket around the f prime. But the way I see it, it's pretty well defined. But I'm just warning you about the order of things here. I guess some people would start worrying whether I'm first taking the square and then differentiating. But I'm not. I'm taking the derivative and then square. Anyway, simplify this. How can we simplify this? F prime squared divided by f prime squared, that's 1. So this is really equal to f of x, f2 primes of x over f prime of x squared. Right? But I already told you that there is an interval between delta 1, minus delta 1 and plus delta 1 such that f prime stays away from 0. Can I now say that g prime is continuous? G prime is really equal to this. F was smooth enough. The only issue is that I'm deriving by the derivative, which could be 0. But if I'm staying in that interval, that should be fine. OK? And taking that up, so that means that g prime is at least continuous on that interval. Yeah.
Isn't part of the algorithm finding a place where?
OK. Think about it. So all of this is to say that g prime is continuous on that interval. But I'm actually going to say that g, equivalently, that g is once differentiable on that interval. Plus delta 1. All right, so we're making some progress here. Because the theorem wanted us to give a g that was once differentiable. And we haven't shown that the derivative is less than 1 and map into itself. We haven't really done any of that big work, right? But we have shown that our function g is nice, which is not obvious because we're dividing by stuff. So we had to make all that argument just to say that this g is OK. Fixed point iteration is not going to freak out too much. Now let me kill this. Actually, we don't need that. Let me ditch that. So now let's go on to that other part. Yeah. Yes, I know I have the thin chalk. It's sometimes not so clear. For example, here are 2 primes. 1 prime. This is a C1. This is not a prime. This is C1, etc. I'll try to think of that. All right, let's move on. Now, here comes another point. G prime at P. I promised you before that was equal to 0. Now let's show that that's the case. It's equal to f of P, f2 primes of P over f single prime of P squared, right? What happens if you plug in P? We're trying to solve fp equals 0. P was defined to be the root you're looking for. This is equal to 0 by construction there. Another way to see that is, of course, going back to those slopes that we played around with and realize that g of x, you have x there with slope 1, and then we're subtracting, by dividing by f prime, we're really subtracting exactly the 1 again, right? But this is a more direct proof that g prime is really equal to 0. So this is indeed the case. 0 derivative at the root. Good. And now comes one of those other analysis arguments here. That means that there must exist a delta. And I'm going to say that it's not sticking out of that delta 1 from before, such that g prime for all x's in that interval is less than or equal to k. For x in pi p minus delta p plus delta. OK, and here you can choose k whatever you want. But of course, we're going to choose it to be a number less than 1. OK, now can you buy this? We need a little figure for this. I'm going to draw a function. OK? And that function is actually going to be g prime of x. We just showed that if you plug in p into g prime, you get a 0 out. So that's good. Now, the theorem wants us to prove that there is an interval around p of size delta, plus minus delta, such that g prime stays away from 1. Do you see again that if the function is nice, that has to be the case? You pick the delta. All I'm saying is that if it were to go up to 1 and minus 1, that would certainly not be OK, right? But then I just pick a smaller delta. So there will be a delta such that I stay within the boundaries of 1. And you can make it as small as you want by just getting closer, because it's equal to 0 at the root. So the smaller you pick it, the better you're k. And this is, by the way, the reason intuitively that Newton works so well, that the closer you get, the smaller that k number gets. But all I'm trying to show now is that you can certainly choose it such that it never goes up to 1 plus minus 1. Again, this comes from definition of continuity, that if you have a continuous function that is equal to 0 at the point, and then it's going to be 1 at some other point, it has to go through all these other values in between. Any series converging to this point here, by a delta epsilon proof, pick epsilon equal to this k value, less than 1, and it will give you a delta such that the function stays within that. Otherwise, it wouldn't have the limit of 0 as it goes to p. So again, that's the little analysis part. But I think it's fairly clear from that description. So now we're getting somewhere. We have a lot of things going on here. We have shown the g prime. We haven't quite shown that it maps into itself. Otherwise, we've done everything. We just need to show that it maps to itself. So I'm going to kill that. So that's the first step that I wanted to do, actually. So I mentioned before, it just seems like if something has a 0 derivative at a point, it seems like I should be able to zoom in so it maps to itself, right? Because it's flat. It has a 0 derivative, right? Suppose it was exactly a straight or a horizontal line, a constant. Then, of course, it would map to itself for any numbers. Because you plug in p, it gets out p. But you know, the closer I get, the more it approximates that horizontal line. So that's kind of the idea. That if it's really equal to that, it can't go too far away from there. The way we show it more formally is, of course, the mean value theorem. I'm going to kill this, but we can draw another figure. So last point here before the ending. By the mean value theorem. And then we have these arguments that we made all the time with the fixed points. We look at how close gx is to p. The idea here is that I'm going to do a bunch of stuff and say that this is less than the previous value, x minus p. That means that it contracts. For each step, you're getting closer to p. You realize what that means? If I had a box, I should have kept my box. I'll draw a new box here. The fixed point box. Oops, it has to, of course, go there, right? OK, I want to show that it stays in the box. If I show that for any number here, and there's a p in the middle, if I show that for any number here, x, so we have p and we have x. And I take a fixed point iteration, and we call the new result g of x, of course, right, by this spiral thing. If I show that I'm getting closer to this, it has to be there or maybe there, right? But it has to stay inside the box. That's another way to saying it stays inside the box. Only way to leave that box would be to go further away from p than I started. So if I can do here that this is less than or equal to even, but I'm going to do less than x minus p, I'm fine. And that's the same thing as we used to do for the fixed point. So this is the same tricks that we used before. You turn the p into a g of p, right? Remember that trick? Because it is a fixed point. So it's g of p. And then you say that this is equal to g prime at some psi between x and p times the jump in x minus p. And we already talked about this g prime and said that it could be less than or equal to k times x minus p. And then you choose this k to be less than 1, which means that now this is strictly less than x minus p. So that's all I wanted to show, that the g of x that you compute, the next step, this guy here, is closer to p than the previous step, than the previous x. Yeah.
Can you just explain how g prime
Oh, this step here. Let's see. From here, we just differentiated G prime. So G is, so it all starts from there. That's G, right? Here. So G prime is 1 minus f prime, this expression. We simplified it and it became fx f prime. Oh, I see, OK. And yeah, why is it equal to 0? All these things are nice. This is not 0. F of p is equal to 0. Yeah, because p is a root. P is what you're looking for. Good question, yeah. The reason this is 0 is that f of p is 0, right? And we use that all the time, so that's an important point. All right, so let's just conclude this to say that that shows it maps into itself. It means that if you take an x between this, in this interval, you have that x minus p will be less than delta, of course. So we start with an x inside the interval, namely that you're not going further away from p than delta. But then I just told you that this means that g of x minus p is even closer to delta. But in particular, all I need to know that it's also within delta. That's the same thing as mapping to itself. That is g maps this interval, p minus delta, comma p plus delta, into itself. All right? So now we're done. The fixed point theorem now gives us that the iterations Pn from n goes to 1 to infinity converges. Okay, for any point inside the interval. Yeah. Well, the k, I'm setting k. I never said it. I never wrote it explicitly. Since we choose a k less than 1. So yeah, when I write k, it's kind of in this setting, I kind of mean a number less than 1. Yeah. No, it has to be that, of course. Otherwise, this is what the fixed point iteration was. Let me go through it again. We've studied. You've done, for simple examples in your homework, so you've done this procedure. I'm just doing it for another g, and it's a little bit more abstract because I don't have g. It's written in terms of some f. And all we need to do is to do the same thing, but just try to work with the general f and f primes, right? So if you go through all these steps, for you guys, it was rarely an issue about continuity and differentiability, because they were just well-defined functions, right? I don't know what you had. You had some 2 over x cubed type stuff, right? I mean, the continuity issue was not a big deal. Here it is a big deal. So we had to work hard to show that g is actually differentiable in some interval. And here comes the first disappointment. The interval is not a number. It is a number, but it's not a constructive number. It's some delta 1 that you don't know what it is. Okay? So all this was just to argue that, you know, first of all, you're allowed to divide by f prime, because it stays away from 0 for some delta. That was that argument. And next, we could move over to say that the derivative is small enough. And we did that by saying that it's clearly equal to 0 at the root, which means that there must be another delta within the previous delta 1 such that it's less than 1. If a function is equal to 0, it can certainly be equal to 1 a little bit away, but you can always stop before then, and that's your delta. Because it has to go from 0 to 1, or minus 1. That's kind of the argument. Finally, that implies mapping into itself by a maybe lengthy argument, but intuitive way was, again, that if it's really flat, it's hard to leave the box. Okay? And that comes out precisely as it did from the fixed point iteration through the mean value theorem, that you multiply by, roughly you multiply by a k each time, or less. Which means, of course, that the k is less than 1, you stay within the box. There's no way g of x could go further away from p than where you start at x. So wherever you are, you're getting closer to p. You can't leave the box. That's the same thing as saying it maps into itself, and you have everything you need. It's a little tricky. Go through it, and I mean, it's not. It just feels unnecessarily long. But if you think about it, we have to show all these steps in order to get somewhere. All right? So that's kind of the main Newton result. People often cite this result in a very negative sense. People ask, Newton is, I don't know if you know how big Newton is. It's really used in so many big huge codes running on supercomputers, solving a lot of important things out there. Okay, and people are obviously concerned about the issue of whether this is going to happen. That would be, pretty embarrassing if that happened when it was trying to solve for some important parameter in some nuclear reactor or something. So people don't like this. And unfortunately, there is no theorem guaranteeing that it's going to work. So people often mention this theorem in a funny way. It's kind of the mathematician's way of life of saying, look, we know that it's going to work. We just can't tell you how. We don't know this delta. But we kind of know that it will work. And it's your fault. You have to be close enough, right? So it's a very negative. It's not a very constructive theorem. But at least it says that if you don't converge, and you start closer and closer and closer to the true solution, to the root, at some point it will converge. Okay? This is not true about, remember fixed point applied to this function? So first of all, we did fixed point about this, and that worked fine, right? That was my vanilla problem. But then I turned it into the inverse, and I said, that's the same equation, but it didn't work, right? And it even didn't work when I started epsilon away from the true root, because the spiral kept on expanding. What did I do? Fixed. Let's see if I have it in the history. Oh, I don't have it. Fixed point. Plot. What did we do? G, we started at 1. No, we started really close to it. What else? Did I need an interval? Yeah. Remember this? Let me start even closer. What is the root? 0.76 something? You see, I'm starting really close, and it's blowing up. So if you think that the theorem we just proved about Newton is just crap because it doesn't tell you how close, there are a lot of methods that are unstable. You start as close as you wish. I think even in the Windows calculator, I started like with 30 digits, right? And you could tell that it was blowing up. So bad methods don't have that property. So maybe that's a reason to be happy. So think about it. It's an important theorem, at least conceptually. Moving on. Any questions on this? Is it clear? So you know how we like to present the method, say what's good about it, but also what's bad. Clearly, I told you what's bad. It might blow up. That's really bad. Bisection can be much more stable than this. And actually, let me just mention a little bit about your program assignment. And I'm sure you guys are going to have questions as we get closer, and we'll get back to the programming assignment. But this is a good time to just tell you that now you have everything you need to know in order to start doing this. All right, can you see that? In this assignment, we will address two issues with the bisection method and the Newton method. Okay? What was one of the issues with bisection? Well, we're going to combine them. So the first issue with the bisection was that we needed an interval, a, b, where f, on one side it was negative and the other side positive, right? Okay, that's kind of hard for someone to figure out. I mean, we're not going to get away from the point that you need to tell where to kind of look, like Newton. But it would be nice to also find an interval doing that. So that's the first thing. The other thing with bisection is that converged very slowly, compared to Newton that needed 3 iterations. So here you're going to write a fancy solver that combines the two IDs. So I'm telling you, I'm giving you pretty strict guidelines. I'm describing it to you in words what to do, and you have to code it in MATLAB. Okay? It can be a little difficult, but just ask questions and you'll figure it out. The first function is meant to solve that first issue. How can you find an a and b with different signs? Starting only from some x0. And I just made this algorithm up, and it's not perfect. You can make it fail, and that would be great because it shows understanding. I just made something up. So what it's doing is the following. Well, let's say you start by ab equals right at x0. Well, that's not good because it's not even an interval, so that's not going to work. Okay? Then I'm going to move away delta x, which starts at 10 to the minus 3. Now I have an interval around your x0. And then you check it. Okay? And if you're fine, then you terminate. That's step 2. Okay? Actually, I'm not doing that. I'm moving just the a to the left. And then I'm adding the dx to the b. Then I double it, and I keep on doing this. You see, it's kind of adaptive, so maybe it has to go a whole step away. It's going to take many steps to do it. But it seems like if a function really goes from negative to positive, it might find a value. It's easy to find counterexamples. But this is what you're going to do. So at least it has some good things going for it. It will only take a value and it will grow. This is like a bunch of lines of MATLAB code. It's a loop. You have to keep track of this dx. A few issues. Start early if you're uncertain about the programming. Then I'm asking you to write a function Newton bisection, which is doing this combined method. And it takes the usual suspects here. The a of b, of course, going to come from this function before. And it's doing some complicated method. What was the issue with Newton? The issue was that it could blow up. Bisection never blew up. Remember? It converged slowly, but never blew up. So how do we combine them? Well, this is what I came up with. Take a Newton step. If it blows up, which I detect by saying you left a comma b, then you freak out, cancel, and do bisection instead. That's the amazing method I'm proposing. This is not necessarily the best, but there are cases when it can do well, right? So you start at your point. You try to do a Newton step, because after all, Newton is what we like. If you left a comma b, you got to reject that step, because we don't want to leave a comma b. And then you go to the midpoint instead, and you do a bisection method. And this is really just a bisection method. So in words, that's all. If I wanted to do a harder problem set, I'm not saying it's easy, but if I wanted to make it super hard, I could describe what I just said in words. Write a combined method, try a Newton step. If it leaves the region, do bisection, repeat. That's the entire method. So it's fairly easy. You should be able to see those pieces now. Just try to illustrate that in code. In problems 3 and 4, I just ask you to do all this. Run it on some function that I made up, and plot how it progresses. And ideally here, I think for the case I chose, it will do a little bit of mixture. It will try a little Newton, then bisection, and it will do a little bit of both. At the end, what do you think it's going to do when it gets closer to the root? Newton or bisection? Newton, right? Newton has this global issue if you're far away, which bisection can rescue, right? So likely it's going to be more Newton at the end. At the same time, when it gets to Newton, it's going to converge in 2 or 3 iterations. So, and then finally, just doing it again with a lot of starting values to see what's going on. Kind of fun. Anyway, has anyone started? Oh, good, very good. Anyone finished? Is it working? Kind of. At least one of them? Yeah. OK, that's cool. So about test cases, clearly I give you some test cases, right? Like in this case, the sine x minus e to the minus x. But you got to make up simple test cases, too. I mean, this is not difficult. You just do the x minus cos that I just did, or just make things up. X squared minus 2. So you can compute the square root of 2. You'll find examples. Anyway, a few more things. Another drawback with Newton is that it needs a derivative. And I mentioned that as well. And this can be a big problem. What can you do if you don't have the derivative? Well, it says so in the slide, but you read that, and I'll make a little drawing. Suppose you really, really do not want to compute the derivative. What can you do? You can do the so-called secant method. The way it works is the following. You have a function, and you're looking for p. But you're starting over here. P0. And by the way, this is a great example where Newton would freak out because I'm close to that. But it doesn't matter here now, because the secant method does not compute derivatives. Instead, it asks you to start with 2 points. And maybe that point is here. And it's not really like bisection that it insists that it has different signs. I did draw it like that now. Sorry, P1. I did draw it like that now, but it could be that P1 is here. OK? But the method does not have derivative. What do you think it does? It approximates the derivative by the straight line between the 2 last points. So it draws a line like this. OK? And the intersection of that line is equal to your P2. Which is the same thing as saying that you're really doing Newton standing here. Sorry, you're standing here and doing Newton. But the derivative is not the true derivative here, because then you would be doing that. Instead, you approximate the derivative by drawing a straight line to your old point P0. It's a derivative-free version of Newton, and it's not as good as Newton, but it doesn't need the derivative. The equations are pretty straightforward. I would say we approximate the derivative as P1 by the slope f of P1 minus f of P0 over P1 minus P0. Right? And then we apply Newton to that. So P2 is P1 minus f of P1. And remember, Newton wants us to divide by f prime, which we don't want to compute, so we replace it by that. So here we get P1 minus P0 divided by f of P1 minus f of P0. That's the whole method. Up there, you have it in n form because you keep on going. And remember, what do you think I do next? So I get a new value P2. What's the next step? I still need two values, right? Do I have two values? I don't have a P3. You're, of course, now called the P1 the old point. So you have 2 points. You forget about P0, but now you do this guy and that guy. And that's your new one. After this gives you the P3. Now, of course, you ditch that guy, and you draw a straight line here. It's going to do funky things, this method. But this is P4, etc. You'll see. You have a few exercises in the homework about this, and you'll see how it works. It's obviously completely straightforward to do. The properties are a little iffy. Someone asked, what is my calculator doing? And the answer is kind of this. Or the answer is, I don't know. I'm guessing that it's... so this regular falsi is quite popular. I think it's something like that. But I'm not going to discuss it too much now. It's a little similar to what I'm asking you to do in the program assignment, making sure that you don't leave the interval. This secant can really blow up just as much as Newton. It can do a lot of bad things depending on how you pick the points. So I don't really know what's going on in the calculator. Obviously, they all do different things, but these are methods to do. But anyway, the secant is completely straightforward. You can actually show that it converges slightly slower than Newton. If you don't mind, let me go on here with this material. We'll do a little more of the theory on Thursday. I just want to tell you some of the punchlines of these theorems here. Confusing notation. We used to define rate of convergence, and you used the order notation for that. I'm now going to define order of convergence. And they're, of course, related, but the order is a particular number here that tells you on a grander scale, like exactly how quickly. There is something called quadratic convergence that Newton has. And we want to try to put a strict definition on what that means. So here's what you're doing. And it will remind you of the rate of convergence, but in a slightly different way. So you have a sequence Pn, and it converges to a number P. That's true about most things we've done, right? Now, that means that Pn plus 1 minus P goes to 0. And Pn minus P also goes to 0, right? Now, clearly, it also means that Pn plus 1 minus P has to be smaller than Pn minus P. So this is really the case. If you forget about the alpha power there and just take it equal to 1, this looks an awful lot like the fixed point stuff we've been doing. Suppose you keep on multiplying Pn minus P by k every step, like we did here. Remember, we always say that the next one, this is kind of in fixed point iteration Pn plus 1, right? Minus P is less than the previous one, which would be Pn minus P. We always say those things, right? That, of course, means that this limit would be a number that in this case would be less than 1, and it would converge. Yeah? Which one? 1? The lambda, you mean? Not for alpha equals 1 necessarily. So let's do a simple example. Yeah, it's actually it's a short definition, but it's quite difficult to see exactly what's going on. So let me show you a simple linear convergent thing similar to with the fixed point stuff. So that would be, for example, Pn plus 1 equals Pn plus 1 half. And we ask ourselves, what's the order of convergence of that thing? If it does converge, did you have a question about this in the homework? Fibonacci stuff. That's the reason I put that there. Not that we know that it does converge, but if it does converge, of course, you can take limits of both sides and get x's here and realize that at 1 seems to be the limit. Because if you plug in 1 here, you get 1 plus 1 over 2 equals 1, right? Now, could still mean that, my example of our coast, that it blows up if you get a little bit that it's unstable. But anyway, if it does converge, it seems to be 1. It will converge, though. But what is the order of convergence? In order to find that, you look at this limit here. As n goes to infinity, of Pn plus 1 minus 1, Pn minus 1 to the alpha. All right? And you plug in the expression, and you're getting what? You're getting Pn plus 1 half minus 1 absolute over Pn minus 1 absolute. And what is this? This is, let me do one more step. So why don't we take out the halves from there? And what you get left then is a Pn minus 1 over Pn minus 1. And I'm forgetting my alphas. And now it's time to stop and think a little bit. Because remember the definition here of order of convergence, so that you can choose this alpha, and actually you want to make as strong statement as you can. So usually we want to maximize the alpha. So when you ask what is the order of convergence, it would be great if you could say alpha equals 2. Can I say alpha equals 2? No, because then I end up dividing by something that blows up as we go to the limit. I just took out this from the numerator. What did I do? No, because I took out the half. Isn't this Pn plus 1 half minus 1? That's Pn half minus a half. I should have done it slower. I'm sorry, I'm writing this very cryptically here. It's Pn, then it's plus 1, and divided by 2, right? So this whole thing is Pn half minus 1 half. Because it's plus a half minus 1. And then I take out that half, and I get Pn minus 1. Did I mess that up? It says Pn plus 1. This is Pn half plus a half minus 1. So it's Pn half minus a half. I think it's right, but I've made mistakes before, so thanks for checking this. Anyway, assuming I did it right, why do you need to choose alpha in order for this limit to exist? What is the largest you can choose it? You can choose it to be 0, but that's not a strong statement because it's not even convergent, right? But as you see, you can choose it to be equal to 1. OK? So then we say that this is equal to a half with alpha equals to 1, which fits the theorem. And it says that we have alpha order 1 convergence to the limit, and that lambda happens to be equal to a half. Roughly, it means this is kind of all the thing we did for fixed point iteration. We multiplied by k all the time. I think I need to show you a better example in order to see the difference, because you're not impressed. So let's do a quadratic one. Again, simple made-up thing. And this is that magic about Newton, why it's so much better than anything else, that it has this other property. OK, so here's another example. Pn plus 1 equals, what am I trying to do? Equals, let's do 2Pn square minus 4Pn plus 3. If it converges, it seems like it would have a limit of 1, because if you plug in 1 everywhere, you get 2 minus 4 plus 3, which is 1. Doesn't mean that it will convert. In fact, for some starting values, it will not. But OK, that's just what it would. So suppose it converges to 1. At what order of convergence would it converge? Play the same game. If you don't mind, I'm going to skip the limit. I'm going to look at Pn plus 1 minus 1 over Pn minus 1 to the alpha. I'm going to do exactly what I did before and plug in this expression, the definition of the scheme, minus 4Pn plus 3. And I have to subtract a 1. And then I'm going to divide by Pn minus 1 to the alpha. Now I simplify a little bit, and I realize I can take out the 2 up there, and left is Pn square minus 2Pn plus 1. I'm still dividing by Pn minus 1 to the alpha. What alpha can I choose now? Let me do a simplification for you guys. That's Pn minus 1 square. Now, of course, I can still choose alpha equals to 1, but I can choose better. I cannot make it larger than 2. Then the limit as Pn goes to infinity will blow up, right? But if I choose it equal to 2, I will have a limit here. This will approach 2 as n goes to infinity for alpha equals 2, which is quadratic convergent compared to linear convergence here. All right, let's just do it. So what was the first one? So let's start at somewhere like 1.3 and do a lot of digits. Okay? The first one I said was take p plus 1 half. You see, I'm doing the thing I always like to do. I throw away all the n's and n plus 1. I just call it all p. That's a computer way to do it. Forget the past. And it takes a step. And you can see this is actually quite instructive. It's quite a stupid iteration. It's going towards 1, right? And it really just went halfway closer. It divided the error by 2. That's the 2 in the limit here. This is kind of a stupid series because it's exactly equal to 2. But if you keep on going, it divides that error by 2, right? So every iteration takes you a factor 2 closer to the limit. That's what linear convergence means. Alpha equals 1. You multiply, and if you think about the definition, that's exactly what it says. If alpha is equal to 1, it says every iteration is a factor of lambda closer to the previous iteration. That's how simple it is. And it converges, and it's linear convergence, and we're not very impressed. Want to do the other one? Let's go back to 1.3. And what was that? 2 times p squared minus 4 times p plus 3. All right? Actually, it starts off worse. Typical, again, think about Newton. It could do really poorly in the beginning. It might not even work. I think at 1.5 it would blow up. But it looks like it's going to save. It went closer. But we're so far from the limit, we can't really make a statement. Now it's, again, not too much better than the previous one. But look now. Keeps on dividing by 2. But there are things happening. Now it seems to divide by 80, right, in one step. And now it seems to divide by 10,000 in one step. And now it's there with all 16 digits, except the last one. That's amazing. That's a huge difference from just multiplying by a half. In fact, it's really hard to beat. Even if this was 10 to the minus 3, this other guy would win in the end, right? And that's what quadratic convergence is about. That not only do you multiply by a constant lambda, you take a power alpha of the previous error. Think about it. That's the definition of these things. But it's the two important cases, linearly and quadratically convergent. And we want to make a statement about this. And I'm telling you the punchline here is that basically Newton has quadratic convergence under the right circumstances. Here are some theorems that we'll prove later, but you can think about them for now. All the usual conditions that you've seen from before, the only new thing to think about is that if g prime at p is not 0, remember this was not Newton, right? But it's probably true about most other cases you've done. Then you have linear convergence of the fixed point iteration. Okay? So that's a nice statement. It tells you it's a negative statement. Remember, we proved already before that fixed point iteration converges. Now we say a little bit disappointing that it's only linear. In fact, the word only there tells you that it's a disappointment. Okay? And the reason is that the derivative of p is not 0. And then, of course, we follow up with a positive statement, but it's a little cryptic. But it's basically saying that the key thing is that g prime of p is equal to 0. But we also need to say that the second derivative doesn't blow up. And we also don't know the interval. So there are a bunch of issues. But then you have that it converges at least quadratically. So it's really easy to summarize these. I mean, there are technical details. But in short, the whole thing is what we said about the proof with Newton. You need a 0 derivative of the g at the fixed point. But this is really strictly saying that that's the only way to get quadratic convergence. And if you don't, you're in trouble. On Thursday, I will go back to this and look at it, but it's, from understanding them, this is what we need. Let's look at Newton then. Here's an alternative. I promised you an alternative derivation of Newton's method. Remember, we played around with x minus 3 times f, x minus 1 times f, and we looked at different ones. How about the following problem? X minus something times f, and then we try to choose something to give us what we want. Because now we know what we want, namely 0 derivative. OK? So if you do this, you can just differentiate, and this phi ends up being primed. You get an equation coming out of it. And you can see that you have to choose this phi of p equals to 1 over f prime of p, which is Newton's method. And this is, I don't know if you appreciate it, but it has nothing to do with those triangles and slopes and tangents. It, of course, ends up being the same method. But it really just goes back to our proofs about fixed point, saying that fixed point is amazing if you have a 0 derivative. Now let's create a fixed point iteration that has a 0 derivative. It's not practically important. You already know what Newton was. It doesn't change that. It's just understanding. There is also another little issue, namely the multiplicity. So this is the x squared problem I talked about before. And if I just want to give you a variant of Newton method that can happen, let's say we do the x squared. OK, simplest function in the world, right? F equals x squared. What is Newton going to do? We need to differentiate from my function. That's 2 times x. Newton table wanted f df, and it wanted an initial point, let's say 1, and it wanted a number of iterations. All right, what do you think about this? Let's do more iterations. It is converging to 0. The root of f of x squared is equal to 0, right? What do you feel about the rate of convergence? Sorry, what do you feel about the order of convergence? If you look at the errors here, you see that they're almost exactly dividing by 2 each step, right? That is linear. You should just look at that and say that's linear convergence, as opposed to the other cases when it's just 3 or 4 steps and it just blew it all up. Something goes wrong for fx equals x squared. And what goes wrong, we know that our theorems don't apply, because f prime is 0, and we didn't allow that, right? So there is actually a way to save that. And it's described here. You define a new method. So if you look at the method down here at the end, this is the funky type of expression you can form to save this situation and recover the quadratic convergence. And it's a nice little trick that you actually apply these iterations on a different function, fx over f prime. But that's the trick that we're doing here. But there is a possibility of figuring this out. So you need to know when you look for root if it has a 0 derivative or not. And if it has, you might need to change the iteration. I think you have a lot for starting with the homework. I did not cover something called Aitken's method, but you can read up on that. And on Thursday, for sure, I'll cover it all, and you'll be on track. Thank you.